My name is Jo Clark and I'm hosting the 3 webinars this week. I will just kick off by giving a brief introduction to the event, and then I'll hand over to the first of our speakers. So we believe that a whole system approach to materials is essential to accelerating decarbonisation to net zero. And this runs right from the manufacture of the fundamental materials to the technologies and the way they are used, and to their eventual end of life. And steel, which is heavily featured in our research, offers a perfect example of decarbonisation and circularity of materials that is possible. So the projects you will hear from are well positioned to work across that whole system, and they're coming together as a project called Switch Connect to make our research more accessible. So this series of 30-minute webinars presents 3 examples from our research across the system. Yesterday, we heard about the fundamentals of steel manufacture. Today, we will hear about the development and use of solar energy technologies. And finally, tomorrow, planning for the end of their useful life. Each webinar will include a short presentation, and there will be an opportunity for questions at the end. Please do type any questions that you have during the seminar into the Q&A box, and we can pick these up at the end. So I'll now hand over to Dr. Silvia Villarroya-Lidon, ATIP Programme Manager, for an introduction to the project, and Dr. Chung Tsoi for a technical talk on emerging photovoltaics for aerospace applications.
Perfect. Thank you, Jo. Thank you, and hello to everybody. Okay. So what I'm going to do, I'm going to give you a brief introduction to ATIP, this integrated photovoltaics program, and explain you why we're doing it. So solar PV has a critical role to play in the transition to a low carbon economy, and is projected to grow faster than any other renewable technology. The sector is currently dominated by crystalline silicon, showing market leading efficiencies and long product lifetime and low cost. Normally, silicon PV is very well suited for large-scale solar farms, so for commercial roofing and everything. However, is less well suited for integration into buildings, facades, PV windows, vehicles, some other applications where flexibility, lightweight, and transparency is required. So then we also have thin film technologies, and these are based on semiconductors compounds such as SiC, cadmium telluride, and others. And these technologies have emerged as alternatives. However, they occupy a small segment of the market. I have an example here of a flexible SiC. This was developed by BIPV and specific together. And this is a flexible SiC integrated directly onto steel roofing. It is flexible, it shows good performance, but it's still very expensive, a bit expensive. Then more recently, we also heard lots about the silicon perovskite tandems. This technology will enhance the crystalline silicon value proposition and enable a new technology to enter the mainstream PV. So it will be, again, one of these technologies that it will make it into the market. But then what ATIP is more focused on is this new area that is focused on solution processable organic photovoltaics, what I will call OPV, and perovskite solar cells. These 2 technologies have shown great progress in improving efficiencies in the last few years. And what it is they show greater functionality and more processing flexibility than the silicon technology. So that therefore enables to design, to tune the design to meet the requirements of market applications that they are not very well suited for the current technologies. So within these unique selling points, we need to talk about flexibility, transparency, lightweight, printable, sustainable manufacturing. So this really is the specific properties for these technologies. So with this setting of properties in mind, they are very close aligned with a series of applications of clear technology need. And here I show you some pictures of it. So, for example, PV to be integrated into the built environment, such as semi-transparent glazing, or laminated into steel roofing products. PV integrated into vehicles and cars, PV integrated into the IoT power sources, and I will show you more examples of this later on, and PV integrated on aerospace-related technologies. So there are applications that they require a set of properties that we very much different. So what is ATIP then, and why is ATIP? What are we doing? So the main focus for ATIP is, as the name stands, is application-targeted integrated photovoltaics. And we are a program grant on solar. These EP-SRC program grants are mechanisms to provide flexible funding to world-leading research groups to address significant research challenges. And in our area was to do this solar research, basically. So the project is a £6 million project. It will run for 5 years. It's led by Swansea University and in collaboration with Oxford University and Imperial College. And the vision of ATIP is to deliver the underpinning science and engineering required to demonstrate a scalable next-generation photovoltaics for these non-traditional PV applications. The project is structured in 5 work packages, as you can see in the picture, and the primary objectives are 3. So first is to advance the fundamental understanding of the performance and stability of OPVs and perovskites, to translate this understanding into the development of new materials and devices, so targeting these selected market applications, and then to demonstrate the scale-up and system integration of those in a printed PV platform. The team, the project is led by Professor James Duran and co-directed by Professor Paul Meredith. Myself, I am acting as the program manager, and then we have 10 further co-investigators in the program from Swansea, from Imperial, and from Oxford. And all together with our PDRs and students, we are and aligned researchers, 40 plus researchers aligned with the project in several organizations. Here I'm showing you other relevant funded programs, like you see CERSAM, CPE, obviously specific, SuperGen, Super Solar, that they are all linked to ATIP, and that it creates a comprehensive ecosystem of research and innovation. In addition to this, the program has 11 key industry partners from, as you can see, some NSG, Airbus, Tata, Armor, CISEM, Brazil, and then they cover different parts of the supply chain, but more importantly, they're bringing out wider commercial opportunities. So here I'm showing you a bit of the timeline for ATIP. So it's, as I said, 5-year program, and because it's all driven by applications. So in the end of year 1, we selected 3 priority application targets. And then we will evolve and look at the front runner technology for each of them and focusing maybe 1 or 2 by the end of the project. So one of them I want to emphasize is the application target, as we call it, indoor PV. So photovoltaics for the use under low light or ambient light. So we're talking about high performance, maintenance-free, sustainable, self-powered electronic devices. And this is Internet of Things. So, you know, they are everywhere in our society. It's a market that is growing very quickly. And the energy demand for these devices is constantly increasing as they become very power hungry because they want more data range and more functionality. So therefore, we need to think that we need to develop these smart devices in a sustainable manner. And this is one way is including energy harvesting. So including using a PV, photovoltaics, as the ambient light energy source to provide the electricity necessary. So in that way, these devices become wireless, they don't need grid connection, they eliminate the use of batteries, and then which altogether reduces the environmental impact and improves the user experience. So here I'm showing you some of the specific applications for these IoTs where they can be PV powered, so we can use them as gas sensors, asset tracking, health monitoring devices, infrastructure monitoring, price tags in supermarkets. So it's a very wide range of possibilities there. Then the other area that we are very much focused on is the semi-trans. Sorry. I carry on with the indoor PV. Sorry. The perovskites and OPV are both very well suited for indoor, and this is shown in the graph. As they work, they work good with LED light sources. So our research is mostly focused in improving the efficiencies and improving the overall performance. So material optimization, we do a lot. We work also for the development of indoor measurement protocols, as this is something new, different to the typical one-sun measurements. So we're working on the performance enhancements of OPV, perovskite devices. And finally, we'll work with the overall power management, integrated circuits and customized electronics, so to have the final system integration. Now, yes, so the next application that I want to cover briefly today is the semi-transparent PV. So here, for example, OPV shows some very special properties such as transparency, flexibility, aesthetics, and lightweight. And therefore, this gives us a great potential for using it as a BIPV glazing panels, using in cars, using in greenhouses, but not just only for the power generation, but in this case also to improve the growth of the plants, for example. And then they can be used as a furniture for cities, public infrastructure. So some of the examples that you can see in here. And then this was very interesting, as you can see the OPV evolving research environment in here. So when we started ATIP, OPV was well below, the efficiencies were low, but in the last few years, it's been an increase in significantly in efficiencies. So as you see, when we started to where we are now, even higher now. So it's again one of the focus of our project, and the research aspects of the program is mostly based on material development and device optimization. And then just to finish off, the third application target that we're looking at is aerospace PV, but I'm not going to go into much detail into this because I'm going to leave it to my colleague, Chung, to follow up with his presentation. So I will take some questions later. Thank you.
Thanks, Silvia.
Thank you.
Sorry, just a moment.
That's okay.
Let me check. Right. Can you see it?
Yes, that's great.
Okay. Right. Thank you. So I'm going to follow up from what Silvia mentioned. So about emerging solar cells for aerospace applications. I'll try to make it brief because of the time to give you some introduction. So what is solar cell for aerospace is very simple. It's very similar to the solar cell used on Earth. The difference is just the solar cell now is at outer space. So the light spectrum and the light intensity will be different compared to on Earth. So we call it AM0. And basically it has higher light intensity, more UV, more visible photons, more near infrared photons. And why solar cells for aerospace? There are mainly two types of application I can think of. One is this called high altitude shadow satellites. So it's more like the body of this planet structure is all covered by solar cells, and so it can be all powered by the solar cells and launched to high altitude for like communication or surveillance purpose but it can reduce the cost compared with launching a satellite in the outer space. And the other one is more like the real space application. It's like, for example, so the solar cell to power the satellite, or for deep space mission, this one to Jupiter. But one of the things I think will be very interesting to introduce today is about the concept of space-based solar power, which is the idea is to put the solar cell the outer space, collect the power from the sun, and then beam back the energy to the earth. And although it sounds like quite like science fiction, but actually a number of governments, including the UK government, is taking more serious about this concept. And just to give you a brief introduction about the status of solar cells for aerospace. So traditionally, silicon solar cells are used for outer space at the beginning, right? Just like for application on Earth. And then nowadays, basically, gallium arsenide-based multi-junction solar cells are used for outer space because they have much higher efficiency. They are more stable, right? So our question is there any potential solar cell technology or material system which can has high specific power and low stored volume? So high specific power means that the power generated per weight of the solar cell. So we want it to be higher because the weight of the solar cell is an important factor, particularly for aerospace application. And the low stored volume means probably like low stored volume. So if the solar cell can be made flexible, and then you can roll it, and then you can use less space for the launching shuttle. And then after it launched, hopefully it can be rolled out and use the solar cells. So we are thinking about these two important parameters. And so now I explain why perovskite solar cell could be very interesting for this aerospace application. So basically, we also work on organic solar cells, but because of time, I'll focus on the perovskite solar cells. And as I mentioned before, so they have high specific power. So I think they're in the lab, the specific power is about 1 order of magnitude higher than the state of the art in organic solar cells. And they can be made highly flexible. And the stability problem regarding to oxygen and humidity can be significantly reduced because in the outer space, basically it's vacuum, right? So it can be good for the stability. And the quality is more important than cost, particularly for space application. And perovskite solar cells have the potential to be low cost, but even we increase the cost a little bit, but improve the stability. I think for aerospace application is still very attractive. Right, so I just give you an example about our study. This is about the proton bombardment. So one of the important issues is about the high energy particles and photons in the space. So particularly for proton, so we study the proton bombardment of perovskite solar cells. So I won't go to the technical detail too much, just give you the main message. So basically we make the solar cells, right? And then we measure the performance under AM 1.5G, which is more like the spectrum on Earth. And then under AM0, which is the light spectrum in space. So our study here showed that if we use this so-called AZO transparent bottom electrode, we can make a pretty decent solar cell with good power conversion efficiency. Even for AM0, the efficiency is still pretty good, for single junction perovskite solar cell using this electrode. And then we bombard the material with proton with energy about 150 kilo electron volt with different fluence, which means number of particles per centimeter square. And then you can see this is just the optical transmittance spectrum of the bare quartz and with the AZO. And you can see they're very similar, even up to the highest proton fluence. So it is consistent that the AZO electrode we used here is pretty proton stable. And for more detail, you can find from this publication. Then we plot a graph about the remaining factor of the device parameter against the proton fluences. So you can see this, the power conversion efficiency basically is still maintained quite similar to the control device up to 10 to the power 13 protons per centimeter square. And then it starts to degrade. And if we look at the device parameter, it's mainly due to the short circuit current density and the field factor, which drop quite significantly at high fluences. So the degradations start at about 10 to the power 14 protons per centimeter square, but it's already excellent stability against proton at this energy, because for like gallium arsenide solar cell, it can already degrade quite a lot, even at 10 to the power 12 protons per centimeter square. So it's pretty exciting for this result. And then we try to understand what caused the degradation at 10 to the power 14 protons per centimeter square. So we do some characterization. Basically, this spectrum just showing that the external quantum efficiency, the degradation follow very similarly to the drop of the short circuit current density. And then we think the degradation is likely due to the whole transporting layer rather than the perovskite itself, because when we do XRD study on the perovskite, there's basically no observable change in the crystal structure. So we start to look at the organic whole transporting layer. And this one is just showing the Raman spectrum. Basically, you can see the spectrum of the whole transporting layer is quite similar up to 10 to the power 13 protons per centimeter square. Pretty consistent with the good stability at this fluence level. But when you go to like higher fluences, you can start to see the drop in the intensity, and which match with the degradation. So we think it's not the perovskite degrade, which even makes it even more interesting, right? Because perovskite is the active layer, and so it's more likely it's due to the organic whole transporting layer. And this is just a study to show that at higher fluences, we need two exponential fits to fit the curve for this transient photovoltaic measurement. And basically, we need an additional fit, which is a faster recombination, charge recombination. And this could be attributed to the interfacial recombination and could be consistent with the degradation of the spiral layer, which affect the interface between the perovskite and the spiral, the whole transporting layer. And in summary, I think perovskite solar cells could be very interesting for aerospace application. It's just start in this couple of years, so there's still many things to explore. And particularly the concept about the space-based solar power, I think perovskite solar cell could be very interesting for this concept. But of course, there are some problems, as you may imagine. One is about the stability issue. So there are more UV photons in the space, more extreme temperatures, and also a lot of high energy particles and photons. So this issue need to be studied well, and if there are any problem, need to be dealt with. And then the other thing is to further enhance the specific power. So the main contribution of the weight of the solar cell, at least in the lab, is the weight of the substrate and the encapsulation. Right, so we need to replace it with thinner, lighter substrates and encapsulation to further enhance the specific power. So finally, I think it's about the absolute efficiency. So the specific power is important, but the absolute power conversion efficiency is also important. So I think we can follow the similar concept, like for inorganic solar cell. We can try. People are trying to develop more higher efficiency tandem perovskite based solar cells. So just to acknowledge our sponsor, particularly Airbus, and also our collaborator internally, and also with the Tsoi Beam Center. And this work is highly related to ATIPs, and actually we have two other publications on perovskite solar cell for space using mesoporous carbon electrode, and also organic solar cell under proton bombardment through AT projects. Right. Thank you.
Thanks both. Really fascinating insight into your research and exciting developments in the space world. I can't see any questions in the Q&A box at the moment, so if anyone does have any, please pop them in. We are a little short on time. Sorry for my technical hiccup earlier. I just wondered, Silvia, if I could ask, are there any opportunities for others to engage in the ATIP program, both for industry and research organizations?
Yes, of course. We always welcome more collaborations. So from an industrial point of view, yes, as you see, this is application driven. So we are very much looking forward to work with industry to know what are the technical specifications that they need. So we need end users, we need different industry in different parts of the supply chain. So absolutely, yes. And then in the research, in the more academic perspective as well. So of course you see that we have already Oxford University, Imperial College, and we actually invited some other early stage career researchers to join in as a research associates. So yes, always welcome for more discussions and collaborations. Absolutely, yes.
Brilliant. On that, actually, we've now got a couple of questions. So Francisco is asking, are you carrying out the experiments running simulations? If yes, what software do you use and where do you get the refractive index of materials? And is it possible to collaborate with the project? So obviously it is possible to collaborate with the project. Could one of you maybe pop your email address in the chat so that someone can get in touch directly?
Yeah.
Yes, going back to the main question, are you carrying out the experiments running simulations? And what software are you using?
Right. Yes, we have a little bit simulation. Basically, the simulation is related to where are the protons in the device structure. So, for example, are the protons mainly at the active perovskite layer or at the interlayer, which is important as well, the distribution. And sorry about that, I forget the software. There's a software which is free for public, so people can use it, and then they can input the parameters, and it can calculate about the distribution of the protons in each layer.
Okay. Thank you.
Okay.
Are there any master's programs with funding for this? Do we know?
There is not such a master program aligned with the project. However, we are as Swansea University Imperial College, we are looking into the possibilities to put something together for as a CDT on solar or something. So we will, yes, we will like to follow up in discussion with this. But as such, there is no master programs with funding.
Okay. We're running slightly over, but I'll just ask one more question. Are you working on the recycling aspect and the end of life considerations for indoor PV? This might tie into tomorrow's presentation.
Yes, yes, absolutely. And yeah, tomorrow presentation is run by Matthew Davis. So yes, this is a very important part of the work, circular economy, so taking this approach to things from the very beginning all the way to the end of life. So yes, we do look at the LCA and the cost analysis, and also there is a circular economy. Yes, the answer is yes.
Right. So we should hear more about that tomorrow.
Yes, yes, exactly.
Brilliant. Okay, well, we have run slightly over and there are no other questions in the Q&A or chat. So I think that just leaves me to say thank you very much, both of you, and hope everybody enjoyed, and possibly we'll see you tomorrow at our next webinar. Thanks all.
Thank you.
Thank you.
Bye.
Bye.
Okay.